We're back again. And now we want to talk about the technique of substitution as applied to finding indefinite integrals, and it also will have application when we start doing definite integrals. The technique really relies upon the chain rule for its definition, and you remember the chain rule from when we were studying derivatives. If we need to take the derivative of a composition of functions, which is f acting upon g, after g has acted upon x, that's a composition, then I can find the derivative of f of g of x with respect to x by taking the derivative of the composition f of g of x with respect to g, and then the derivative of g with respect to x. So if you're a little shaky on that, you need to go back and review the section on chain rule in the earlier part of the course where we were talking about derivatives. But now we can notice that applying the integral operator, if I would just integrate on both sides of this equality, I would have the integral of the derivative, I'll write the whole thing out, df of g of x dx dx, and that's equal to the integral df of g of x dx times d of g of x dx, and then a dx over here. Now this can be simplified, and the first thing we see is this is the integral of a derivative. This is the integral of the derivative of f of g of x. The indefinite integral is looking for the function whose derivative would be the argument here. Well, I mean, it's almost redundant to say it. What would I have to differentiate to get the derivative of f of g of x? Clearly f of g of x. So on the left-hand side, I've got f of g of x. And on the right-hand side, well, I'm not going to solve this, but I'm going to note that this is the derivative of f of g of x. It's understood that this is the derivative of f with respect to its independent variable, times, and this would be the derivative of g with respect to x dx. Now the method of substitution has to do with solving equations of this form right here. Since we'll be using this to evaluate equations, integral equations that look like this, I think I'm going to take just the time to write this from the opposite direction. So it's f prime g of x g prime x dx will be equal to f of g of x. And that looks maybe even scary, but let's try a couple examples. Let's analyze what we have and try a couple examples, and I think you'll see that it's really a very useful, very powerful technique for finding integrals. So let's talk about just a little bit about what we've got here, though. So here's what we're looking for, and mathematics is an affair of the eye as well as an affair of the hand and mind. And so I see that I have a composition right here. I've got a composition of functions, and it's the derivative of that composition. But what I would recognize would be the composition of functions. And then I have the derivative of the inner function, dx. So those are going to be keys, and those are going to be things that we're going to be looking for. So let's try an example. We want to start with an example that's not too difficult and that really illustrates the point. So I think we'll look at this. Let's look at the integral of 2x e to the x square minus 1 dx. And we want to find out what that's equal to. Now it's an indefinite integral, so what are we looking for? Another way to say this is we're looking for a function whose derivative will be this argument right here. And that's what an antiderivative is. We're looking for a function whose derivative will be this argument here. Now, how does the result we've got here from the chain rule help us? Well, remember we said the structure in here is a composition, and we would also have the derivative of the inner function. So when I look here, I see the e to the x squared minus 1. That's really a composition of functions. I've got two functions. I've got one that maps x into, assuming x is its independent variable, into x squared minus 1, and I have another function that maps its independent variable into e, and these are composed, and that's how I get e to the x squared minus 1. And then I've got another piece. I've got a piece over here, and this piece is the derivative of the inner function. If the inner function is x squared minus 1, its derivative would just be 2x. So I can write this as the integral e to the x squared minus 1 2x dx. It's not necessary to rewrite that, but I think it's going to help, because here's the technique for the integration by substitution. We're going to let u be the inner function. Now I've identified the inner function for you here as x squared minus 1. So that's going to be u. Now again, you're going to have to remember back to the earlier chapters in the course when we were talking about differentials, because now I want to use differentials. So I want the differential on the left and the right hand side, and that's going to be du, that's the differential on the left, is equal to 2x, and I'm going to take the derivative here of a constant, that's going to be 0. So then it becomes a differential when I say, not du, try the eraser out, but dx. Sorry about that. So du is 2x dx. Now look at the structure that we've got right here. I've got e to the u, and the 2x dx is du. So I have equals the integral e to the u du, making the substitution. And this is easy. We know that the integral of e to the u, what do you differentiate to get e to the u? Well, just e to the u. So this is just an e to the u plus an arbitrary constant. And now the final step is to go back to the original variables, because u is just a substitute for x squared minus 1. So this is e to the x squared minus 1 plus a constant c. And you can check and see if that's actually the case, because what we're asserting is that this expression right here is an antiderivative of this expression here. So when we differentiate this, we should get this if it's truly an antiderivative. And I would let you practice that on your own. So we'll do some more exercises in a bit. Thank you.